Okay, here we go on this problem. You might want to check these answers right here to make sure that they're correct before watching the rest of the video. If they are correct and you want to figure out how I got the answers, then keep watching. And I have, for part C, trapezoidal rule for 4 intervals as underestimate and midpoint rule as an overestimate, which leads to this conclusion for part D, and that's C. And in these problems where you're going to use the trapezoid rule or the midpoint rule, you might want to consider finding the second derivative. I don't know if you're allowed to use a graphing calculator to find information about that second derivative, but the truth is that if the curve on the given interval is concave downward, then the trapezoidal rule is an underestimate and the midpoint rule is an overestimate. So we could use this to perhaps determine the concavity of f of x on the original interval. And the truth is that on the interval from 0 to 1, this expression that I've circled in blue here is always negative, which means that the curve is concave downward. So that's how we got these conclusions. So I'm going to go to Desmos and show you that I've graphed the function cosine of x squared on the interval from 0 to 1. I've set a as 0, that's the left-hand endpoint. And then I've gone to the trouble to calculate x sub 0, x sub 1, x sub 2, x sub 3, x sub 4 by adding d sub x, or delta x, the correct number of d sub x's to the starting point A. And by the way, d sub x is, where did I define d sub x? Right here. Oh, it's so 1 minus 0 divided by 4. It's 1/4. And then using the trapezoidal rule, which is right here, delta x over 2 times the quantity f of x sub 0 plus 2f of x sub 1. This is where I get the 0.89576 rounded to 5 decimal places. And I plotted these points, x sub 0, f of x sub 0, so that you can check the values that you get for when you employ the trapezoidal rule. So, for example, f of x sub 1 doubled is 1.996. So that'll help you confirm what you kind of did wrong when you got that 0.79 answer. By the way, the value of the integral, the exact value using the Desmos definite integral function is 0.904. So you can see the trapezoidal rule is an underestimate. And here's the midpoint rule. I get 0.90891 rounded to 5 decimal places. And that's an overestimate. And I did go to the trouble to evaluate these error conditions. And I want to go back to Desmos and go to board 3 and talk about this error bound deal. So when we're using the trapezoidal rule, the only difference between it and the error for a trapezoidal and a midpoint approximation is this 12 here and a 24 here for the midpoint rule. So this kind of shows you that the midpoint rule always has less of an error than the trapezoidal rule because the denominator is bigger for the same number of subintervals. Okay, and then make note of this fact: the graph is concave up the trapezoid approximation is an overestimate, and the midpoint is an underestimate. So here's this red curve, just to give you the idea. It's concave upward. It doesn't really ever turn around here, but it's concave upward, and the trapezoidal rule kind of shows that this leg of the trapezoid gives you this little area above the curve because the curve is concave upward. And if I had a concave downward curve, then I'd be underestimating by this little area right here for the trapezoidal rule. So up trapezoid, over. It's maybe how I would try to memorize that. Up trapezoid, over, and then everything else is opposite. So the midpoint and the trapezoid rules give opposite estimates over or under on the interval from A, B, assuming f of x is concave up or concave down. So if you remember that they are opposites, then you just have to memorize one of them. So I would memorize this one. Up trapezoid O. Up trapezoid O. UTO. Okay. So let's see. Is there anything else we needed to talk about? Oh, yeah. So I've got this Desmos graph that also does Riemann sums. It only uses either the left-hand sum, the right-hand sum, or the midpoint sum. And so here I've got it doing the midpoint sum, and it gives the same exact answer that I got on that when I calculated by the midpoint rule. And there's the definite integral. So I'm going to send you the URL to this Desmos graph. But if I use the left-hand endpoint, this is where when the function is decreasing or increasing, when you're using left or right hand endpoints, that's where you only need the first derivative to determine increasing and decreasing. But if you're using the trapezoid rule or the midpoint rule, you need to find whether the curve is concave up or concave down. Okay, so I'm going to end the video. If you check out these answers and they don't appear to be correct, let me know and we'll figure it out. Okay, there we go.